Okay, now I normally have a rule where I don't solve anything that's not a main line Road to Las Vegas case on YouTube, but I just have to do this one because it's got to be one of the best cases I've done. On first playthrough, I didn't realise how good it was until kind of second playthrough, and you think about the questions a little bit more and find some clever shortcut solutions. So there's some quite instructive stuff I'm going to do in this solve, and for Harry to come up with some of these questions, he is just a genius. This is such a good case. Now the first question, nice and simple, just finding the difference between two times. You can't actually minus one from the other because times in Excel are actually like fractions of a day. So this is 0.12 of a day, which is 3 hours into the day. So because that's a fraction of a day, you need to times by 24 to get the hours, and then times by 60 to get the minutes. So that's a good trick to know. Now we have Alice drinking some drinks. These are emojis of length 2. And every time we drink wine, we double. Every time we drink milk, we reduce by 5 times. And we want to find where we reduce to size 1. So we're going to start at 72. That's given to us in the question. The array is these all split up, but we need to split them into 2s because the emojis are length 2. And the function's going to be lambda a v. If v equals, and then we need one of these wines, so let's just put this as a static value for now, and do, well, that's the milk. So if it equals that, then we do a over 5, otherwise we do a times 2. The question tells us we need to round up to the nearest integer each of these steps, so let's round that up. And what we'll get is we'll get a spill of our size, how our size moves, and we want to find where that goes to 1 or below. So that's just an X match 1 in there, exact match or next smaller item. So that's that one. Now I'm actually going to do the bonus related to this one now, which is here. If Alice drinks 100 glasses of wine in a row, starting from a size of 72, how many glasses of milk will she have to drink to reach a size of 1 or less? Now I think because of the simple case, we believe that Excel can't do big math numbers, but it can, it just doesn't give you the precise digits on the end. So we're saying Alice starts at 72, and she drinks 100 glasses of wine, so 2 times 2 to the power of 100. So that will actually give us a number. It just will have a load of zeros on the ends. The precision isn't there, but you can still do the maths. And we need to divide it by 5 a bunch of times, so that would be 5 to the power of something. So we could divide it by 5, I don't know, to the power of 50. If we've got 100 glasses of wine, maybe we'll try half the number of milk. Okay, we get a really small number. Maybe let's try 30. Okay, we get a big number, so maybe we do it to the power of 40. Okay, 10,000, so it needs to be bigger than 40. 45, that gives us 3. 46 gives us 1. Let's check if it's less than 1, and it is. So the answer is 46. However, I kicked myself on this question because you can just use logarithms. Let's just write it out in an equation so you can see. This is basically 72 times 2 to the power of 100 divided by 5 to the power of n, and we need to solve for n, and that equation equals 1. We're trying to find where it equals 1. So if we times both sides up by 5n, we're just going to get 5 power n when we rearrange that equation. And now, to solve for n, all you need to do is a logarithm of this to base 5. So it's just equals logarithm of 72 times 2 to the power of 100 base 5. And that's going to give us 45.72. So you just need to round up 46 drinks. Super easy, shortcut, and instructive that we don't always need to use big math. So I think Ha, who won the UK Championships, he actually has a long division lambda, which is very complicated, and he used that to solve this question, I think. But you don't actually need to. You can do big math in Excel, you just won't get the precision of digits, and you often don't need it if it's a question where you're going to round to a certain answer. Instructive one, and one to remember for me. Now, my favourite question, a super clever logic puzzle. So, the possible answers to the question are given here, and then the blue bits, the answer for this cannot be the answer to any other question. So, i.e., we need numbers that are unique in this column and only picked from here. However, the pink cells, the answer is the same as one other game in this chapter. Now, thinking logically for a second, if we had 2, which is one of the options, now this needs to be the same as another answer in this chapter. But if 2 was up here, this would no longer be true, because now it is the answer to another game. So all of the duplicates have to be contained within these 4 cells. So we can see we have 11 twice and 13 twice in these cells. So 11 is there and 13 is there. So that has to be the answer to those logically. And that is going to allow us to solve all these other questions, because we can now eliminate these numbers from all of the options. So we have 11 and 13 here, so that must be 19. But let's spill it out. Text split this on the comma and times by 1. That gives us all the numbers. But what we want to do is we want to filter out what we already have. So to filter out what we already have, we're going to say let A be that, filter A where is error, X match A in this whole column here. And when I drag that down, what you'll see is the 11 and 13 disappear from here, and the 9s have disappeared because we've got a 9 in the example, so that leaves us with a 19 here. So basically this is, now you can iteratively, 19 has disappeared, now this has a 17 as an answer, so it kind of will cycle around, so you now have one option to solve each question. However, we want to do it with a formula. So you can actually do this with circular references, so let's just turn it on. So now here's where the genius, like, aha, that's so cool part of this question comes in. I want to say if there's only one element in this array, then give it to us here. When I do that, this is going to turn into a calc error because I've used it, so it disappears from all of here. So I want to say if there's an error, just give us what was in the cell anyway. So I'm going to say if columns of this array equals 1, i.e. there's one thing there, then give that to me. I'm not going to worry about the false condition, it doesn't matter. I'm going to say if error, then just give me what's in the cell already. And as I drag this down, the circular reference is just going to iterate like I showed you manually and solve that with a formula. And that is just a very cool game and solution that iteratively sort of solves itself. Super cool. Okay, the next question, we have a load of puns here and we want to calculate the value of them. So each letter of the alphabet is worth its place in the alphabet. So let's just say alphabet and then sequence of 26, like so. However, if there's a capital letter, then the points are worth double. So we're going to say equals that times 2. So here's an instructive point. If you have two letters like this, one capital and one not capital, if I say equals one equals the other, is that true? Yes, it is. So how do I tell if something is a capital? Well, instead of equals, you can actually use exact. So exact will give you, it's the same as equals, but they have to be exactly the same. So that's actually false. So to tell if something is a capital or not, you can say exact upper and the letter. So if the letter is the same as the upper version of the letter, wrapped in the exact formula, then it's a capital. So let's use that to solve this. So I'm going to say equals let letters be split this down into its letters, and then capitals are going to be exact of the letter is the same as the upper of the letter. And then I am now going to do an XLOOKUP depending whether it's capital or not. So I'm going to say if capital, then XLOOKUP the letter in here and give me the double the points value. If it's not there, give me 0, because symbols are the same as their upper version because there's only one version of them. So the symbols will come up here, I won't find them in my alphabet and I'll spill 0 for them. I'm going to say if not, then I'm going to XLOOKUP the letter in here again, but I'm going to return this column instead, the singular values, and it should do some locking on these things here. That's going to spill out a bunch of numbers. So I just need to wrap the whole thing in sum, and that should be it. So when you know how to determine what a capital letter is, it's actually a reasonably easy question. Now, another super cool question. So we have some pixel art here of the Mad Hatter, and inside the cells we have the RGB value. So 67 red, 110 green, 90 blue. And we want to find which cell in the picture is closest to these values. So let's just flatten the map. That's going to give us all of the cells addresses and their what's in the cells. So we're going to say text split this on the colon, semicolon. Let's just also times it by 1 to get it into numbers. So to find the closest one, we're going to say text split this on the semicolon, and we want to minus off all of these values here. Let's lock that. And then we want to wrap that in absolute to find the absolute value difference, how far it is away. That's going to give us a big spilled array of, well, let's just actually show you what it looks like, because otherwise this might be a bit confusing. It's pretty big, all of the numbers like that. So all we need to do is by row sum that. Sum, and then look up the smallest value. So I'm going to say sort by the addresses, which are here, by that array, and we want them ascending, so we don't actually need that argument. And I want to take the first one there. That's a little trick I've seen in one of Bo's videos. Instead of x looking up the smallest value, you can just sort. Time difference isn't much, but it's still a cool way to do it. We can also do two of the other bonuses now. So what is the sum of all the red RGB elements? That's just going to be the sum of all of these reds. And now this one, another very cool question. So it's asking where the nose of the Cheshire Cat is. So the cat watches over the Mad Hatter's tea party. He isn't visible, but the RGB values can be reapplied as colours. So what that means is, in this image, the RGB values are not real. The image is here, and the RGB values in it don't actually represent the colour in the image, they might represent something else. So you can use some VBA to turn all the colours, but instead of VBA, what I actually did is I said most of, just to investigate what's in this map. And if I just zoom in, you can see that right at the top we have this 255, 255, 255 cell, whereas everything else only appears, 2 or 3 times at max. So let's just remove that out. We want to look for all of the 255s. So let's just highlight this, Control F, we want to look for 255, and then we select them all. Let's find all actually, sorry, and then shift click to the bottom and let's color them black, and we can kind of see what's happening already. We get an image of the cat. So I'm just going to zoom out a bit. Very cool. We can see the nose is just 1 pixel here in cell 090. So again, what a cool and unique bonus. So 090, very cool. Okay, chapter 6 already, flying through this. So we have a bunch of arrows and this little map of cards here. Now this is 4 down and 13 across, so you have 1 of every card. And the idea is you start from the Jack of Hearts, and if you move up, instead of moving off the grid, you actually wrap around to this 7 of Hearts here. So you can also wrap around this way. So we want to start at the Jack of Hearts, follow these arrows, and find what card we end up on. So I kind of did a bit of a cheat way here. One cheat way is you could count the number of up and down arrows and just do the net movement up and down or left and right, and then you have less distance to kind of explore. First thing I'm going to do is just check these arrows are the same as my normal ones, so let's just say unique of those, and then I want to put my arrows here and just copy paste everything as values so I can line them up because they're different characters here. And the way I kind of solve this, a simple way, is I copied this grid a load of times into a new tab. So I said equals vstacks this, and then how many times do I want to stack it? Well, I've got 30 arrows to move in, so I want to have it at least like 60 directions in case the same arrow came up a bunch of times, which it probably won't. So let's just stack it 20 times to be safe. That gives me all of that, and then let's just reduce the size of this grid massively, and then I'm just going to copy paste those values and just copy it a bunch of times here so that we can go left and right as well. And then I want to find a Jack of Hearts somewhere in the middle of the grid and just do all my moves from there so I don't ever go out of bounds. It's just the simplest, quickest way I found to do this. So let's use this one here, which is in Y41. So Y41, we can actually just do it all in here. So let's say reduce. Initial value is Y41. Our array is xlookup all of these individual arrows in here and give me back here. Oh, what have I done there? Press the wrong button. And then our function is lambda a v, move on map from a with v, and that is going to give us our final cell, and then we just want to determine what's in that cell. So I have a addressed contents lambda, which is going to find what's in there. Let's just actually put a bracket around it. There we go. So a fairly quick and cheaty solution there. Okay, question 7 here, we have a maze. I didn't realize, but these borders of the maze actually have a 1 in the cells. The borders are like actually cells and not just formatted borders, which I didn't know in the live thing. The question is that Alice is standing somewhere in the maze. Which card can see her? So cards can see everywhere except through walls, so they can't see past a 1. If I knew that, I would have done this formulaically, but in the real thing, I did it by just copy pasting manually where the cards could see. It didn't take too long, a couple of minutes, and then I had the map filled out and I could determine what's in the given cell. However, now I know that there's 1s in there, let's do it with the formula. I'm actually going to use a lambda that I haven't shown before, but I I guess I will at some point, equals 2 row, well, I guess you're going to see it a little bit now. So I have a block out map lambda, which I could probably use for this, but this is an easier way, I think. So what this lambda does is, it's called priority movement. It gives me a start cell and a map. And I will have a list of arrows that are priorities and a list of blockers. So basically we'll move along the first arrow until we hit a blocker. If we can't move with that arrow because a blocker's there, then we'll move with the next arrow in priority order. So it will spill out a path based on kind of priorities. So I can say equals priority movement. My map is this hedge maze, so let's just make sure we get all of it. And my start cell is this, and let's just lock that to the column. And my priority arrow is this, so this takes multiple arrows and in priority order, but I only have one. My blockers are the number 1, and my steps, let's just do 50 steps. I have an allow loops argument, say if I can loop. So basically, as I follow this arrow, the 5 of hearts is there, this outer bound is basically where I hit a 1, I've hit my blocker, and there's no other arrows for me to use as a priority. So I just want to take the second column of that. So let's do that. And then I want to filter out any zeros or out of bounds. So I will say, let A be that. Filter A where A is not 0 and A is not out of bounds. And there we go. And then these are going to have nothing, so because there's not a card there. So I'm going to then say, if error, I can do it in the filter argument, which I never actually use, but I should probably do that. So if there's an error, I just have blank. And then what I can do is I can just concatenate those to get the answer. So let's just drag that down. And then say equals concat all of this stuff. And we are done. This one actually is a safe spot, and you're supposed to write 0 for safe spots, so that's easy to see. Epilogue here, you just write fin to get the final point once you're finished. I should really do that at the end, but whatever. Yeah, I do kind of want to make my block out map lambda maybe a little better, because I can do custom directions on it already. Maybe it's worth adapting, not sure. Anyway, we have 2 more hard bonuses. Now this one is a bit of another aha moment for me, which I really loved. And the question asks, if you start a Jack of Hearts and take 30 random movement arrows, which is the least likely heart that you will end up in? Okay, so let's try and explain my thought process of how I arrived at the answer to this one. So if the arrows come up an equal likely number of times, then they are most likely to cancel each other out. You're likely, if you've got 30 arrows, you're likely to get, 30 divided by 4, 7.5 arrows each, so they all net off. So the most likely place you'll land at is actually back where you started. But this isn't necessarily true, because 30 doesn't divide by 4 nicely. If you divide 30 by 4, you're going to have a remainder of 2. So 28 of those arrows, on average, are going to cancel each other out, and you're going to have 2 left. So the most likely cards are going to be 2 steps away. So 1, 2, 1, 2, and then if we went up, it would be 1, 2 to this 5 of diamonds, and so on. So because they all cancel out, the cards that are least likely to come up are those that are further away. So you'd think things over this end of the board, however, because of this wraparound mechanic, that's not always the case. So when I was thinking about this, I first built it by doing this. So I did the circular reference. So this is our 0th spot, and then I want to do minimum of everything around that spot plus 1, and just quickly propagate that to this map, and make sure we're starting at 0. But I want to do this wraparound. So this is actually a number 2 because we have the wraparound. This is actually a number 1 because of the wraparound. And this 5, we can actually go 1, 2, and then up. So this becomes a 3. And then everything kind of maps out. So these are our distances to everywhere. So the furthest distances away are these 2 cards. However, the question is asking us which heart card is furthest away. Now, one crucial piece of logic that most people will miss is because you're doing 30 arrows, it's always an even number of steps. So you can never land on an odd number of movements. So these odd numbers, you can never land on them. So the question is, what hearts can you get to in an even number of moves? So I'm just going to copy this as values, and let's try and just get rid of everything that's not a heart quickly. So I have a card details lambda here. I want to say x lookup these in here, give me the suit, and then if that's hearts equals hearts, give me that, otherwise give me blank. Let's just do that. So these are all of our hearts, how far they are away. So I actually want to know, for the odd numbers, what's the quickest way I can get there in even steps, because it's only even steps that matter. Now, to go between odd and even, because there's 4 rows here, if you use the wraparound up and down, you're always going to still be on an odd or even number. And because there's 13 across, which is an odd number, if you do the wraparound across to the right, you're going to swap between an odd and even position. So the quickest way to get to this was 5 by doing our wraparound. However, to make it an even number, we'd go the other way. So 1, 2, 3, 4, 5, 6, 7, 8. So that would be 8 steps away. Anything else odd? This one here, this Queen of Hearts, is odd. So we could go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's actually quite far. Then we have this odd number, this Ace of Hearts. So 1, 2, 3, 4, 5. We need to do some wraparound. So we need to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 10 away. And now everything's even other than this 7 of Hearts. And this is actually the hardest one to get to. And the reason is because it's the furthest card to the right that's an odd number. So we need to do the wraparound to turn it from an odd to an even. So it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 when we go up to use the wraparound there. So this 7 of Hearts, knowing that we have to take an even number of steps to get anywhere, is the most unlikely card because it's further away from the starting position, because all arrows will on average cancel each other out. So it's going to have to be a very weird combination of arrows to take you 14 steps in that direction. So 7 of Hearts is our least likely card. Final bonus, and then we'll talk about the epic final riddle. So this is saying that the caterpillar does not ask the last 4 questions, and then how many possible ways can you fill this in? So if I delete these out, and then we get back to our whole circular reference thing. Now we don't have any numbers to eliminate, so I haven't actually solved this one. I know Dim has a video where he will solve it, but my thought process when I started to do it was basically there's 3 options here, so I could put an 8 in, and then there's still a maximum of 3 options. So I wanted to kind of go down the path of when do I always get the maximum number of options. So if I put a 5 in here, I'd have 3 times 3, I've still got 3 options, times 3, times 3, so I could put a 13 there. So I've got, 3 to the power 4 there. And then I've got 2 options, so 16, and then we still haven't iterated, so 12, we've still got 2 options for stuff, and then it all iterates, it all solves itself. I tried to do like different routes with different combinations and add them up, but I just couldn't get there. So I watched Dim's video, figure out how to solve that. And with that said, spoiler warning, let's go on to the final riddle. So within this spreadsheet is a load of hidden stuff that you wouldn't have seen. And apparently Lana Banana is hiding in this spreadsheet. And we have a riddle here to try and find where she is. So my story of trying to solve this, I spent like an hour on it last night, went a bit mad, couldn't find it, and then it just kind of clicked for me today, and I solved it. So it says that Lana's hiding in this spreadsheet somewhere, famous in some circles, but no squares. So I started looking for all of the circles in this case. I started looking at the images. So this image is called This Is Not Lana in Disguise. This circle here has it in the formula, substitute, this is not a banana tart, it's a jam tart, Lana is nowhere here. Then, I started doing stuff like Control F for Lana on values in the workbook, find all, I found 2. So one of them is actually under this picture, Lana's not here. One of them's in this header, Lana's not here. This one, we have, Lana is not here, but it was a good thought. On the Mad Hatter's riddle, we have some comments down here, not here. We also have, I think there's some even more down, she's not down here. Then I started going into these pictures, substitute, she's not under my hat. This picture is actually called I'm Not a Monkey, and you can even go to the shape format and the accessibility alternate text, and it will say, nice try, but not here. Now I knew that she couldn't be somewhere in the spreadsheet, she'd have to be in somewhere of the metadata of the file. So if I go to even the file and go to properties, we'll see that on the details it says bananas rule, but I'm not here. It's just everywhere that you look, so there's so many places. Then I found there's a hidden tab, your monkey princess in another castle. Then I went to Visual Basic to see if there's any very hidden tabs, and there is a very hidden sheet here, so I made that visible, and then I should be able to see the very hidden sheet. Lana's not here. Maybe you could actually try solving the riddle. I looked at a bunch of places and realised, okay, I need to solve this riddle. There's no way to do it without solving the riddle. I thought about this riddle a lot. So, a curse to booming drover crows, unmanacled Monet loopy, as prime scoops go, better treat by void without duty, and to fact cunning witches over 4 score is just kooky. Bees are all wrong, their life is Ella spooky. So I thought I needed to unmuddle this riddle, because at the bottom here it says don't not fail to muddle the meaning of this riddle, but then it says don't not fail to muddle the meaning of this riddle, which means keep it muddled. Then I thought about, you know, the Alice in Wonderland books, and thought about maybe we're all just busy bees trying to work, go about our lives, and maybe this is a philosophical thing that, you know, busy bees are all wrong and it's all a mad chase for nothingness because nothing really matters in the end, which is kind of true, but, you know, who cares? And then Harry told me that's not the intention of a philosophical goose chase to be a busy bee with no end result. Then I got thinking about what's important in this riddle. So we have the word prime, and there's, you know, I like prime numbers, and this is a very mathsy case, so, you know, Harry's a good mathematician, so something to do with prime numbers. And then I saw this emoji, so why is this bee different? So I thought, what can a bee represent? Well, a bee can represent the insect, or it could represent a letter, and bananas have a letter bananas in. So I started thinking, okay, prime numbers and letters, why don't I take the letters out of this that are in the prime number positions? So that occurred to me quite quickly today to try, and that was actually what I needed to do. So let's just pull out a list of prime numbers here. Let's call that. And what do I want? I want this split into letters. So first we need to get the text out of this image. So let's do that. And then just put it down there. And then let's do split that text down. And then I want a sequence of the length of this. And then I want to index it on this, so equals index this on this. I actually don't need this sequence, I don't think. So I got kind of nowhere with this. This was a space, so I thought, okay, I must have to remove spaces. So let's substitute out spaces. Substitute space for nothing. And then I saw custom document property. So I was like, okay, custom document properties. And I had to actually Google where to find this because it's somewhere I've never been in Excel before. But if you go to File, Info, you will see a load more places where Lana is not. Banana's rule, but not here. Lana's not here, so on and so on. If you click this properties thing, you can go Advanced Properties to see more properties. Lana is not here. Banana's rule, but I'm not here. Custom, so this has got to be where it is. Custom name, Lana Banana. So I found it, and the password is all caps Bananarama. Amazing. You know, I don't even know how to edit all this stuff. Harry's obviously just an Excel genius. So the password is Bananarama, and that is the answer to the final riddle. Wow, what a case. And that chase at the end is so good. Just insane the amount of work gone into this, and it was so satisfying to crack this riddle and be the first one to do it in the end. Anyway, back to the regular schedule of uploading my kind of tutorial videos next, I think, and I hope you enjoyed.